Hello everyone, it's Juan here. In previous videos I have explained how to accelerate Java parallel applications on GPUs using TornadoVM. But what if you don't have a GPU? Can you still use the CPU for hardware acceleration? Well, the answer is yes, you can do it. All you need is a compatible OpenCL runtime. So in this video, I will explain how to get access by using Intel CPUs and the Intel oneAPI toolkit. This toolkit not only gives us access to CPUs and GPUs, but also to FPGAs. So in this video, I will explain how to do this and how to configure it and run a few examples. So if you're interested, stay with me. Let's do it.
Let's start with the installation and configuration of the Intel oneAPI based toolkit. So to reach this, I will put a link down below, but essentially you just search in any search engine Intel oneAPI download, and probably you will get this website. So it's very easy to install. You just select your OS. In my case, it's Linux, and your distribution. In my case, I always prefer to do it offline installer. It's a matter of preference, and depending on the installer you choose, you will prompt it with the instructions. So if I select offline installer, then it will prompt it to do these commands. So we download the installer and then we run it. So I already did so, and if I jump to the terminal, I have it over here in my bin directory Intel oneAPI, and the only thing we do is to run it with sudo command. So we do that, and then it just pops up the typical GUI installer and steps for the installation. So you click continue. In my case, I already installed it, so it will prompt it to modify or uninstall. I have a few versions of it, by the way, and that's my location. If you don't modify anything, that's the default location, and we will use this for the configuration part. So if it's the first time you launch this, you just prompt next, 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 and yeah, you will install the oneAPI. So once this is done, and assuming you have Tornado already installed with OpenCL, if you missed that, I have another video in which I explain in detail how to get Tornado installed with different backends. For this one, remember to access the CPU, we're gonna use the OpenCL one, and already configure Tornado to run with OpenCL. So this is my directory of TornadoVM, and if I type tornado -- devices just to check the devices I can use from the Tornado side, as you can see, I have two on my system. I have an NVIDIA GPU 3070 and an Intel integrated graphics. But we just installed oneAPI and the CPU is not here. Why is this? Well, we need to invoke a configuration script, basically a setup for the environment. To do so, we just type source opt Intel oneAPI setVars. This is if you install oneAPI in the default location. If you install oneAPI in another folder, in another location, just follow that installation or that path, let's say. So if I do this, it will load the environment for oneAPI. And now if I type again tornado -- devices, I will get more. Still, I'm gonna see the NVIDIA 3070 as before. I'm gonna see also the Intel integrated graphics as before, but now I also have the Intel CPU, that's my CPU. And I even have the FPGA in emulation mode. So note that on my system, on my setup, I don't have an FPGA. However, and this is related to oneAPI gives you the option to run FPGA in emulation mode, even if you don't have the FPGA. So for this tutorial, for this video, I'm gonna focus on these two with emphasis on the CPU. So I'm gonna run now an example and show you some performance numbers just to kick the discussion and to show you the potential of using Tornado on CPUs. So the example I'm gonna use is the same as previous videos or previous tutorials. If you missed that, I'm gonna put a link down below. It's a GitHub repo with plenty of examples in TornadoVM. And let's jump to it. So I'm gonna use the one called a blur filter. Basically this is an application, very simple application that takes an input JPEG image and applies a blur filter. So just to give you an idea what it does, I'm gonna show you the input image in a second. Yes, there we go. Let me remove this directory. Input image is this one in this case, okay? It's an image I took a few years ago in Rome, right? And the output image is something like this. It applies a blur effect. Let me open it. So as you can see, it's very aggressive. It's like a pixelated, but it's actually blur, effect on it. That's the output image. So in case you wonder, let's go to the input image and see the dimensions, because that's the input data sizes. If we go to properties, quite likely image properties, perhaps. Yes. So the input image is around 5,000 pixels by 3,800 pixels. That's the input data size, and Tornado will map it to that number of threads internally. If you choose a GPU, if you choose a CPU, it will use all the cores, try to map all these data size. So let's go back to the application. Again, I will put a link down below for this code, so you can follow along, or you can even modify it and do some performance testing, etc. And I'm not going to explain in detail the programming model, because I have a separate video just to explain how Tornado could be programmed, and I use actually a very similar example, if not the same. But essentially what we're looking for is this. So we have a task graph. This task, we decompose it into different tasks. So the task graph is composed of 3 different tasks. Each task maps a channel. Red channel, green channel, a blue channel. Then we create the execution plan, and then in the benchmarking mode, we just call multiple times execute just to measure the timing for each iteration. So that's down here. If you choose the Tornado flag, okay, we'll run the Tornado side. It will run in a loop the execution plan.execute. Right. So let's jump now to the terminal and show you how this could be run. So I'm gonna jump now to a second terminal over here. I'm gonna open Tornado -- devices. Again, because I haven't loaded the Intel oneAPI environment just yet, I'm not gonna see the Intel CPU. So let's do that again. So source opt Intel oneAPI set vars. Now if I type -- devices, I should see again all the devices, including the CPU. So know that, as we have discussed in previous videos, Tornado selects different indexes for different devices, and is ordered by device index and backend. So backend : device index. If you want to access the CPU, the indexes are 0:2 in my configuration, in my setup. That might differ in your setup depending on the devices you have installed, if that makes sense. So in my configuration, device 02 should map to the Intel CPU. So let's do that. I'm gonna run this application, and I'm gonna run it with this command. I'm gonna enable thread info, right, to tell me where this code is running. And I have the application over here, target, TornadoVM examples, and the application is called this one. And then I pass the Tornado flag. This is specific for this application I'm running, right? Because I have an option to select multi-threaded, sequential, and then start comparing times, let's say, in benchmarking mode. And then I have the option to pass the device in which I'm gonna run. So if I don't pass anything, it will select the default device. If I do it and I run it, and I have the thread info, it's gonna select the default. Remember, my default was the NVIDIA GPU, right? So if I want to change, remember that my CPU was in device equal 0, 2. If I do that and run it, Now, Tornado is running on the multi-core CPU using OpenCL, the OpenCL backend, right? That's the amount of seconds per iteration. So look at the first one though. So we start, that's the first 3 tasks in a task graph. It took 5.5 seconds, and then it went down to 5 seconds. So remember that Tornado, the first time that you run, it will compile all Java methods that are attached to the task graph down to the technology you choose, the backend you choose. In this case, it's OpenCL C code. After the compilation is done, then the code will be reused. So this is the time that took the compilation part plus more things in probably metadata attached to it. So this will run for a few iterations, already finished. It took around 5.2, 5.4. It's actually faster, but keep in mind that I'm sharing the screen, I have many applications open, etc. Just for reference, let's run the multi-threaded. So in this application, in this particular example, I have the flag of empty to run with Java streams. So if I run it, just to have a quick comparison, it will take a while to set up, to read the image, and then start running, and then it will run a few iterations. So we can see that the first took 5.8 seconds. Probably it's gonna be down a bit because the JIT compiler will kick in, etc. So 5.7 seconds and so on. Again, keep in mind that I'm sharing the screen and I have many applications open. So in general, we see that Tornado is faster running on the same hardware as Java multi-threaded, so same CPU, right? Just by using the OpenCL backend. So in fact, how much faster? Well, in this particular set of execution, let me cut it here. This is not a real benchmark, okay? This is just to give you an idea. So let's try to have this. Let's try a small one, or the minimum one could be this one, I think. And let's try this one for Tornado. So Tornado is around 10% faster right now in my setup with all these windows open, etc. Which is not bad. So the difference comes from, well, many places could be. One of them, or the obvious one, is that the streams, Java streams, is dispatched through the Java runtime. While the OpenCL, once the application is translated, is compiled down to OpenCL, then it's the OpenCL runtime that dispatches the application, the entire application. So we have 2 different runtimes here. Both of them measure end-to-end, but 2 different runtimes. Apart from that, OpenCL can be considered as a domain-specific language. And just because the way it's programmed, it could be easier for compilers like an Intel compiler to vectorize. So you can get a bit of a speed ups because of vectorization. So if you wonder about the speed ups in a benchmark mode environment, I actually run this beforehand with JMH framework. Let me show you the numbers. I have it here, logs JMH. And as you can see here, the Java streams take 5.9 seconds in average. This benchmark ran for almost 18 minutes, by the way. After, a few iterations for warm up and a few iterations for measuring the actual performance. And the Tornado version took 5 seconds. So this is a different speed up of 17%. So usually if you have a big data application and is data oriented, going through something like OpenCL can give you extra speed up compared to Java setup. And I also compare it with Java sequential. So this is just the same application, running with Java. Java quite likely will try to vectorize code, etc., will optimize the code. And we see that the Java stream versions is around 12 times faster, while the Tornado version is 14 times faster. Obviously, when we talk about performance, we need to talk about setup, right? So I will put the description of the machine and the input size on screen. And I will also add a blog post that you can check all numbers and the setup that I'm using. Again, my purpose of this video is not to show just performance. In this case, we have performance in Tornado. It doesn't have to be always that case, but it's just to show the potential of running data parallel applications with Tornado on CPUs as well, and the advantages that you can get. That's all. Right, with this, let's jump now to the execution on FPGAs. So ideally, I should be able to run this application on FPGA with Tornado. However, keep in mind that Tornado is still an academic project. The development is ongoing, so it's improving. And unfortunately, there's a limitation of running multiple tasks in a task graph on a FPGA. So this cannot be done right now, but we could run, we can run a task graph with one task. There's another example here. Let's take that one. For example, Mandelbrot. Mandelbrot is a typical fractal application, and it generates actually an image, something like this. This is the Mandelbrot set, right? So this code generates or produces that image. And this application is implemented using one task in a task graph. It's over here. The definition is over here. Let me put this a bit bigger. The definition is over here. So we have a task graph and we have one task, only one task. So we can run this on the FPGA, even in the emulation mode, and I'm gonna show you how. So let's jump to the terminal. And the first thing we need to do is, in order to use the FPGA, let's take a look at the indexes first. So if I run Tornado devices, the FPGA is accessible in my setup, in my machine, using indexes 0:3. That's the Intel FPGA emulation platform. So I'm going to use this. But to use the FPGA, the compilation in TornadoVM is a bit different. And this is because to run on the FPGA, compared to other systems or to other devices, is also a bit different, even if you do it in C++. So we need to add a flag called CL context emulator device Intel FPGA equal to 1. And then we just call Tornado as usual. So Tornado, I'm gonna print the kernel perhaps. I'm gonna also add the thread info, which means give information about the device it's running. And then I just call application. So target is called in here, TornadoVM examples. Tornado. So if I do that and I run it, quite likely it's gonna run on the default device because we haven't specified anything different, right? Indeed, it's running on the default device in my system, which is the NVIDIA 3070. So let's change the device. In Tornado, remember, we have a flag called S0. So it's a JVM flag. And we need to specify we need to specify the name of the task graph plus the name of the task dot device. In the case of my FPGA, is called 03. So how do we know this? Because this is how you name your task graph. If I go back to the code and the Mandelbrot application, the task graph is created, the name given is S0 and the task is S0. So I just put these two in here, S0 T0 dot device and then the device I index. So backend index colon device index. So if I do that, now it's running on the FPGA emulation mode, right? So one thing, even here is measuring times, never measure in emulation mode. Okay, emulation mode, following the Intel documentation, is executing in a single threaded. It's just to check that you can run on the FPGA potentially. What it does is it creates a directory called FPGA source comp, and in here it creates the binary. In FPGA terminology is called bitstream, and this is the actual bitstream. So this is a binary. If I open it, well, we will see just a binary format file. And that's the file that will be potentially loaded into the FPGA if we have the real FPGA. And it will also create a few files, the source file that was compiled, and it will print the error file if it's any error, and the output for the compiler part. And the difference is that the compiler is is the FPGA compiler from Intel in this case. So that's a command to generate the bit stream, if you are interested. And how Tornado knows these flags? Well, that's interesting. So Tornado, by default, knows how to connect with Intel FPGA and Xilinx FPGA. How do we know? Because Tornado has a file in the SDK. If we go back to our installation of TornadoVM, and if we go to the directory called bin SDK etc, there is a file called Intel oneAPI FPGA.conf. So, if I open it, then we see that the file, the folder name to include all the bit streams, the compiler to use, and the device to use. Right? You can change that if you want to, and even if you can bring your own configuration file. In that case, Tornado has the option, this one, right? And you pass here your equal your file, right? It's in the style of JVM options, so something like this, right? In the application, so something like that, and you bring your file .json or whatever conf, right? With that, you can tune the compiler to use if you want to optimize the flags to optimize for the FPGA, etc., etc. So as I say, the FPGA compilation workflow is a bit different than the rest of the devices, a bit more complex because it involves two more steps: the configuration file and the environment variable, depending on if you are using the emulation mode or not. And that's all, right? So one more thing, remember that to run on the FPGA, I put this flag. Let me go back. I put this flag up front. This flag is only if you use the emulation mode for Intel. Otherwise, you just don't set this flag, okay? You just call Tornado as usual. Unfortunately, I don't have a real FPGA in my system, so I cannot show you. Hopefully in the future, if I get access to one, I will be happy to make a video. So let me know in the comments down below if you want to see that happen in the future.
Right, so that's all I have for today. So hopefully you will have a better understanding of how Tornado can be used not only to run on GPUs, but also for CPUs and even FPGAs. So if you like this content and you want to see more like this, I'm preparing more tutorials that I will be published in the near future. And with that, I conclude the video. Happy coding and see you soon.